Shouldn't have said that. The topic I'm gonna run through is we've looked at and I'm gonna show who we are. Just a second. We've looked at the performance of using the ZFS as a store for a parallel file system on top, and we use the Fraunhofer parallel file system. You're not really familiar with it, so I'm gonna spend a few words on it shortly. So first, looking at use cases, there's a big disclaimer. I should actually bold type it. Some performance data we retrieved, and some going forward. Now, we're an HPC center, so we do high performance computing. We do that for science users in multiple Austrian universities. We've got, one can already say, 3 clusters, because this is, as you see, is from yesterday. That's a matter of fact. The third one is being built as we speak. We mostly have HPC, standard HPC codes. So there are codes for weather forecasting, and there are codes for various physics applications, finite element analysis, and so on. And they usually run as message passing over MPI, and this is InfiniBand connected nodes. So that's basically the environment. That's a point of note in here just for the environment is will be the largest oil cooled. These are as an oil pump HPC site in Europe very shortly. So this is actual boards being put into oil. So this is something with some novelty value. Now the use cases we look at here for a CFS is scoped to be around archiving, around user data backup, and there's some priorities in terms of what we look at, and this is not necessarily the weighted list, but the reliability is really much on top. Performance is not with these use cases not really the top one at all. So we look at it's got to be reliable, stable. It's got to be nicely manageable, and so on. The environments will all be using 0.62 Linux. So we love Linux. We're scientific Linux users, and we're all over Linux. For the parallel file system called Fraunhofer Global File System, GFS, as it used to be called, and now it's called BigFS. There's a B symbol apparently which now comes with it. So we're using a parallel file system coming from the quote-unquote makers of MP3. And this is a file system which you can think of separate storage nodes, separate metadata nodes, made to really allow for multi-gigabyte throughput for users such as genomics and what comes. So this scales to very large, 40, 50, 60, 70, 80, and the curve is very nice. So this is a very high performance file system. So the questions we looked at first, and I'll say it very openly, we were quite negative on it. So we looking at this, is this stable, 0.62 for our purposes? Is the stack stable? Is it performing? And so that the null hypothesis were actually no. So we just look at it as an exploratory testing. Now, disclaimer for the data is, and you're gonna see we thoroughly rejected this sort of hypothesis. It turned out to be doing extremely well, actually, for most part. The disclaimer is, of course, this is work in progress, non-finished, just a snapshot. It's mostly synthetic workloads. So just one is called a real workload, and last but not least, it's non-optimized. That's for sure. So there's a long list of optimizations which can be tried as we go. Now, 3 environments. One is these are not huge environments for this testing. One is one blown up server node with a collapsed metadata management with another management tool on it. Then two InfiniBands, most for those tests we only use one though. We have enterprise SSDs in there for the cache and for the L2ARC and what come. Then we do have 8 load creating clients for this environment. And release-wise, again, it's shown before. Second environment is from prior cluster, just for sizing up the testing. It's for old Sunfire nodes, which you see here. No surprises here. The next environment is a server node out of another cluster, which is AMD here. Yes, this is built on RAID for process reasons, and going forward we'll put it on JBOD, of course. And however, we had this on the RAID. The first battery of tests were basically looking at the Gaussian combinations of native file system. We use XFS, sort of as the default native, and ZFS, and remote, not remote, and so on. And with large files and small files, and there is some data. This is basically for orientation. Does this have a laser? Then see if I can. Oh, does this have a laser? No. Basically, what to see from that is the small. I would disregard the small file sizes. We were just seeing early on that of course caches and so matter, but what matters is the large number of files. The performance everywhere is just bad, and however, it's along the lines of the other options, so ZFS being one and the others being similarly not too high, but it's not grossly off. So this is a first thing to see. And then as we go to larger file sizes, the data becomes more interesting. So I would go straight to here. There's a 8 something, almost a terabyte file. Ballpark wise, we're comparing, we're getting into the region of native XFS, and there's some of course local remote differences, but ballpark wise we're coming close. Then here another baseline test where we put only the XFS as backstore, and here, and this is a key figure for us per node. This shows about 3.6 gigabyte per second. So this is again disclaimed in here. This is one way to measure it. Other ways you get different values, but this is close to native performance. What over InfiniBand QDR what you can get. So this is actually the 3.6s might have some cache effect in there. This is very high. Here we have a RAID Z already with 4 tanks with 9 disks, and there comes already the surprise. So again, we were very negatively looking at this at first. So how can this and so on in the stack? But here we're reaching, and this is without any optimization at all. We are reaching about 2.7 gig, 2.2 gig in this configuration, which is pretty good. It's pretty good, very good actually. So this is territory we're in, and this is definitely something in the sort of admissible range. Then, oops. Then here, whoopsie, 2.7, and then here, not sure what the parameters are different. Then here it even goes up to 3.4. I have to look for the test parameters. I don't have them on the slide. RAID Z1.
What's the difference between these two?
I'm trying to figure out what the difference between those two was. I cannot see it on the slide, so I'm afraid I have to go back to the notes. So there must have been a different parameter. I would have to go back to the notes. So there's some parameter different. Obviously, the reading goes up to 3.4. I would believe. No, I couldn't say. I have to go back. Here then there's a stripe of 4 times 8 again nested. Nested, and here with different file sizes, and you can see 2, 4 up to 64 clients, leading to about on the large file size again 2.3 gigs, which is excellent. Which is excellent in here. Just marvelous. So this is the real world Fraunhofer file system layered on top of the nested RAID Z1 2.3 with a single server. Perfect. Here is another test. We used the benchmark tool called IOR. We like to use this for MPI, especially if multiple processes are active. Here is a single case, but this tends to lead to lower values in comparison with other simpler tests. But this is also a very good figure in here, 1 gig, very good figure. Here it becomes a little bit more difficult. No? So here is read-write 100,000 files. The performance, as shown before, is pretty comparably bad as for other file systems or the layered file systems. However, or let me go in the following. Now, last but not least, we did some. I do not show the data here because it's almost it's too good to be true. So we have to go back to doing more measurements. But we did like a 72 disk stripe with all out load on this stripe, and we're basically getting InfiniBand speed on it. So despite the layer, despite with huge files, it's very good. It's very good. Now comes the however. The however is in another test case, we back up user data, so real world data, to another environment. Here we've got about 152 million files on one cluster, so that's quite a bit. The L2ARC and SIL were of course there, enterprise SSDs. Now here's the good part. The compression we're getting is nice, and 1.5 approximately this pace. Now with DDAP enabled, I shall say, and the DDAP, not all files as of measuring this, not all files have actually been on the DDAP. Now, as of measuring this, the small file is performance is metadata side is really an issue. So if you traverse for 152 million files with a recursive LS or concretely, I think a find not minus exact, just a find recursively through the tree, looking at like 10 hours or so, and if you do a find and stat and so on the files, it gets even worse. So this is quite long. So here, however, in this test with the long recursive runs, this was just CFS and not layered on top. So presumably this would not get better with it. Maybe. So here there's room for improvement. So this is really difficult. Yeah.
So this test was not with RAID Z, is there?
This was with. Let me think. This is.
I
we
see
have the hardware RAID.
Sorry,
I have to look in there what the data is. I'm sorry. I'll follow up right up.
So,
then, yeah.
but you were using deduplication, but it wasn't really giving you any benefit in this. workload?
Too early to call. This is so large. It takes so long you have to copy this over, and so more data is coming. But so far, it's not bringing that much of a benefit. So metadata, this is an issue. However, running these things, I mean, think of it. This is 152 million files. This is many double-digit terabytes. So that this runs out of the bed unoptimized, stacking this on each other. This is very nice, and this is well be above expectations. So even on the many file size, this could basically do it. So we saw a very few issues, if at all, and one is that this is a non-issue. This is not an issue, a bug. We just ran into this from the very beginning, that the UDEV, the Linux UDEV messes things up, tiny something. We think we saw a memory leak on the user data backup side. This is now instrumented, not the dtrace or anything, just looking at the memory as it goes along and see if you can reproduce it. And the key thing is one would have expected you layer this, and no side has really adapted anything. It just worked out of the bed. Nice. So what would be of interest going forward from our perspective of operating these things is checksums end to end, of course, not computing them multiple times. So that's one thing. Erasure codes. Oh, we would love this. So if you could do away with RAID and have this all in the distributed file system, the parity information, and then all scattered around the disks, this would be very nice indeed. So this is not a CFS issue. This is more up there, but this would be a nice thing to have. And of course, larger, better small file performance. This is would be nice. Yeah.
Did you measure small file performance without RAID Z?
Let me in comparison without RAID C, just non CFS we did, but without RAID C, I have to go back to the data. I will come right back after the presentation. Here acknowledgements, and so again this was a snapshot of measurements. So far we're very happy, against low expectations, but very happy. We'll go on testing. We haven't done this yet, but we'll be doing bitrot testing. So I'm writing a little tool there to selectively flip bits, put it up then. And we need to do more negative testing. So we have done negative testing. It's not listed here in the slides, but yes, we have done it. Pull the disk, pull the cord, and because reliability is most important first, and it always came back. So the most important is the feeling that you would trust this to be reliable is actually so far so good. But again, we need to do much more negative testing. For that, we need more test automation. So we've written some scripts and so, but this needs more of it. That's it.
May I have a question? What's the availability of FHGFS? So if, I don't know, I might want to use it and give it a run, how can I get it?
Availability in the sense of getting a hold of it.
Yeah, what are my options? Do I have to buy it? Is it open source? Is it closed source? Who do I speak
I'm
to?
not I couldn't say that the as is status, but I believe first of all we're a commercial user of it, but I believe the base use of it is free. I believe, and the client side I believe is open source, and as a commercial user we can get the source of the server, but which is not open source, I believe. But the base usage without any support contractor so is free as far as I understand. Yeah.
And in terms of clients, which kind of clients there are? So there's a Windows client, there's a Linux client, there's a...
This is all Linux.
All Linux, okay. Thanks.
Yep.
So on the scenario you presented, that you used RAID hardware, right?
Right. This again will not. We will not use this rate going forward. But for how should I say? In operations, you go step by step, and things you know very well. You know rate, and you go.
Yeah, because I was thinking about mix and matching these two, because it would obviously benefit more ZFS to use the disks,
Oh,
like the whole disks, not having a single loon exposed from a hardware RAID. Performance-wise, I mean.
Yeah, I mean, performance-wise, it's not necessarily a clear-cut case because it depends on like what hardware is in that RAID. So like, you know, RAID Z obviously, like RAID Z has its own performance issues. And if you have, you know, a beefy piece of hardware RAID that has, you know, some NVRAM that's caching and, you know, it could actually accelerate performance. It's just that you're spending a lot of money on that, right? So cost performance, yeah, you're definitely going to do better with just ZFS on raw disks. But ultimate performance, you know, if you're putting in this additional hardware, it may give you a performance boost.
Think of it also as a question of operationalizing things. So we've got many disks. So we know we have procedures when a disk fails, and with ZFS, all this has to be established first. So this is how we went